Today I'm at the Museum of Contemporary Art in Santa Rosa, California. This is the home museum of Daniel Alberti, sculptor of the stars. No, not movie stars, those stars. Everyone, I would like for you to meet Daniel, who has created many unique sculptures using celestial mechanics. Celestial mechanics is the mathematical calculation of the movement and positions of the planets and other objects in the sky. Daniel even has a personal connection to the sun. Isn't that right, Daniel?
Well, that's right, Derek. But everyone has a connection to the sun. I'm a sculptor, and I like to use the light of the sun and the light of celestial objects to play off the surface of my work. As a young boy, I would often ride my bike over to the California Academy of Sciences to check out the Morrison Planetarium. They had great shows on astronomy, and there was this fantastic pendulum which showed how the Earth rotated on its axis. These are the kind of places that inspired my interest in astronomy and the mysteries of the sun.
Daniel, our show today is about eclipses. What can your sculpture tell us about solar eclipses?
As an artist, I'm fascinated with light and shadow. I love the way light changes during the course of a day, depending upon the position of the Earth to the sun. So I began to sculpt objects that show light and shadow on their surfaces. And over here is a sculpture I recently created. It's my favorite.
That's cool. What is it called?
It's called a shadow catcher. This bowl-like structure focuses natural light as a dot drifting across the sculpture. Watch as the dot passes across the shadow catcher. It's interesting to see how the form travels along the surface of the sculpture, much like the shadow of the moon crossing the Earth's surface. And students can make their own shadow catchers. For directions to make the shadow ball, check out the link at NASA Connect website. Of course, an eclipse is one of nature's most dramatic works of art.
Daniel, thank you very much for sharing your personal story with us.
You're welcome.
Okay, so did you notice Dan uses science and math to create his works? His understanding of form, light, shadow, and space are what makes his sculpture so unique. Let's find out more about these magnificent solar eclipses. Here at the Chabot Science Center in Oakland, California, visitors can explore interactive exhibits that teach about the movements of the planets and their moons around the sun. The movement of the Earth and Moon creates the most powerful display of form, light, shadow, and space in our world, a total solar eclipse. As a total eclipse begins, the moon's shadow approaches from the west. The chill and the sweep of the moon's shadow rushes across the landscape at over 1,600 kilometers per hour. Totality is a phase of the eclipse when the light from the sun is completely blocked from view. The darkness of totality resembles evening twilight affecting living things. The sky near the horizon still appears bright, but sunlight seems gray and weak. The solar eclipse is an amazing sight. But to understand what an eclipse really is, we need to talk to a NASA scientist. But before we do that, here are some questions that your students might want to think about. Why do eclipses occur? What is angular size? What is the path of totality? Why don't we see a total eclipse every moon cycle? This is a great time to pause the tape and discuss these questions. Fred Espenak is one of the world's authorities on eclipses. He works at NASA's Goddard Space Flight Center in Greenbelt, Maryland. He uses computers to make predictions on thousands of eclipses, and he runs NASA's official website on eclipses. These accomplishments and his participation in dozens of eclipse expeditions have earned him the nickname Mr. Eclipse. So let's ask Mr. Eclipse, how can something as small as the moon block out something as big as the sun?
Good question, Derek. A total eclipse of the sun is one of the most awe-inspiring sights in all of nature, and it's all made possible due to the unique geometry in the distances and sizes of the sun and moon as seen from the Earth. As we all know, the moon orbits the Earth and the Earth orbits the sun, and celestial mechanics allows us to calculate these orbits with great precision. When the moon passes between the Earth and the sun, we say that the moon is in the new phase. An eclipse of the sun can only occur when the moon is new. However, not all new moons produce a solar eclipse. The moon's orbit around the Earth is tilted about 5 degrees to the plane of the Earth's orbit around the sun. As a result, the moon spends most of its time either above or below the Earth's orbital plane. the moon passes through the plane only twice during each of its orbits. If the moon also happens to be in the new moon phase when it crosses Earth's orbital plane, then a solar eclipse will occur. Most eclipses are partial because new moon takes place just before or after the moon crosses the orbital plane. But if the timing is right, a total eclipse of the sun occurs just as the center of the moon passes directly in front of the center of the sun. The path that the moon shadow makes over the Earth during a total eclipse is called the path of totality. To see a total eclipse, you must be in the path of totality. As a total solar eclipse begins, a ghostly silhouette looms into view, framed by a white glow that creates a halo around the darkened sun. In the final seconds, the sun's remaining rays shine through deep valleys along the edge of the moon. At the same time, the sun's corona appears, surrounded by the moon's black disk. Before the last bead of sunlight vanishes, the effect resembles a cosmic diamond ring. Suddenly, totality. The bright sun is gone. A black disk surrounded by a pale halo now stands in its place. The sun's corona is the most stunning, most beautiful, and most unexpected feature of a total eclipse. As the outermost layer of the sun's atmosphere, the corona is extremely hot with a temperature of 2 million degrees Celsius. The moons of other planets in our solar system produce eclipses, but none of them have the perfect size fit that total eclipses have from Earth. In some cases, the moons have angular sizes that are much larger than the sun. In other cases, the moons are much too small and too far away to cover the sun. We call this kind of an event a transit. Our NASA Mars rovers have both photographed Martian moons Phobos and Deimos as they transited the sun. Pretty cool. To compare the relative sizes of the Earth, Moon, and Sun, we'll use this basketball and this tennis ball. Let's call this basketball Earth and this tennis ball the Moon. These are the relative sizes of the Earth and Moon to each other. So what do you think we could use to represent the size of the sun? A small car? Think bigger. The sun would be 90 feet in diameter, about the size of this office building. So how is it that this tennis ball-sized moon can block this building-sized sun? The answer is angular size. Angular size is the measure of an angle formed by extending imaginary lines outward from a specific point to span the width of an object. The imaginary lines form a triangle. Angles are measured in degrees. Two objects in space may appear to be the same size if their distances and diameters are proportional, and if they are viewed from the same position on Earth. The diameter of the sun is 400 times larger than the diameter of the moon. But the sun is also 400 times further away from the Earth than the moon is from our planet. If you extend imaginary lines that span these two objects to our viewpoint on Earth, you can see that two similar triangles are formed. The angles formed at the viewpoint are the same for both objects, making the angular size of these objects equal. When these bodies line up exactly, the moon appears to be the same size as the sun, creating a total solar eclipse. This fortunate coincidence is responsible for the perfect fit of the total solar eclipse, one of the most spectacular events you can possibly witness in our solar system.